problem. Spring is attached to the ceiling and pulled down 13 centimeters from equilibrium and released. After 3 seconds, the amplitude is decreased 3 centimeters to 3 centimeters. The spring oscillates 9 times each second. Assume that the amplitude is decreasing exponentially. Find an equation for the distance d. The end of the spring is below the equilibrium in terms of seconds, t. Like the other spring problem, we're going to need to write down an amplitude function. So at the beginning, the initial amplitude is 13. But as time passes, amplitude will change as a function of time. So it says after 3 seconds, amplitude is decreased to 3 centimeters. So we know 13 is the initial value, and we know that there's going to be some coefficient, let's say b to the t, where b is some value, non-zero value, non-negative, non-zero value that we need to solve for. And that is going to be equal to 3 centimeters after 3 seconds. So in other words, we have an equation to solve. 3 is equal to 13b to the 3. So 3 over 13 is b to the 3, or b cubed. We need to take the cube root of each side. So we take cube root of 3 over 13, and that's the base b for our exponential. So our a sub t function looks like 13 cube root 3 over 13 raised to the t. You can also rewrite that as a of t is equal to 13 3 over 13 t divided by 3. So that's our amplitude function. Next, they give us the frequency, f. F is 9. The period is 1 over the frequency. And we can start to write our equation. Here we start at a minimum or maximum, so again we will use cosine function. Writing amplitude function first, 13, 3 over 13, t divided by 3. Cosine, now we need to solve for b, the coefficient of t, 2 pi over b, which implies that b is going to be 18 pi, so 18 pi t. And there's no phase shift here, and there's no transformation up or down, so I don't need to worry about that. So this would be our equation for this spring problem. Thank you for watching.